Hello everyone and welcome back to another video. Today I'm going to be doing an ENM problem again, and it's also to do with the electric field. So if you haven't seen the previous video on the electric field, I'd recommend going and checking that out, unless you're of course familiar with the electric field equation, in which case this should be fine. So we're going to be doing problem 2.5, which is to find the electric field at distance z above the center of a circular loop of radius r that carries a uniform line charge lambda. Now you can see this in figure 2.9. It's just a loop, and we have our charge there at point P. This is our height, and this is our radius. Now, just a short recap of the electric field equation. The electric field of a line charge is E of r is equal to 1 by 4 pi epsilon naught. And then we have the integral of lambda of r prime, which is the electric field, which in this case is uniform, over r square times r hat times dl prime, which is just integrating over the length of the basically in this case the length of the loop. Now we can go to notes. I've prepared a replica of the diagram. I've changed r from small to capital. It's not a very significant difference, but it helps us remember that r is in fact a constant. And with that, we can begin. So let's first write down the electric field equation. So it's 1 by 4 pi epsilon naught, and we have lambda of r prime over r square r hat dl prime. Now with this, let's first write down r, which we know is going to be r prime. It's going to be r minus r prime. So we know that r is going to be z hat, because that's just the location of our charge over here, and r prime is going to be, and this is interesting, so r prime is just going to be the location of an arbitrary point along here, right? So we can say that it's going to be r sine theta for any angle theta along this circle, r sine theta x hat. I'm going to be using x hat instead of I hat, it's the same thing, plus r cos theta y hat. Now this will give us a circle, of course, and we'll be covering every single point on that circle. So this allows us to express in terms of r and theta, which is going to be useful when we're integrating. Anywho, we can now write this r as z hat minus r sine theta x hat minus r cos theta y hat. And we get the magnitude of r is going to be z square plus r square, and r hat is of course r the vector over the magnitude of r, so get z hat minus r sine theta x hat minus r cos theta y hat over the root of z square plus r square. And now we can finally take all of these and whatever is relevant, this and this, and plug it back into our equation here. So okay, let's rewrite that now. We get E of r is equal to 1 by 4 pi epsilon naught. So now we're going to be integrating from 0 to 2 pi, and the reason we're integrating from the reason we're integrating from 0 to 2 pi is because we're going to be integrating along theta, because we know that r is a constant, so we've actually reduced this to a problem with just one variable. So okay, now we know that lambda is just going to be lambda, so we can just write that as lambda, because it's a constant charge, over z square plus r square, because remember we have to square this over here. And now we can take our r hat, which is this very short expression. Oops, that's going to be a cos. And remember, we're integrating over theta. Now what we're going to get here is, because we're integrating from 0 to 2 pi, our integral is going to come out to 2 pi lambda r z over z square plus r square to the 3 by 2, and we're going to get z hat. So this integral is something that we can resolve by just, because we only really have to take these into account. It's a fairly simple integral, and we get this as a result. So that's all for now, and thank you for watching the video.